the requirements of neural signal processing in biomedical implants, especially brain implants. So the main topic of interest to this session is signal processing itself. But when we are implementing signal processing techniques in biomedical implants, we are required to think about the other sides of the story. So we need to have a circuit to realize the signal processing function that we are interested in. Then, as I was talking about, in most of the applications, we need to have real-time streaming of neural signals to the outside. So real-time operation of this hardware is also important. And the other side is the small physical size of the device. We're talking about biomedical implants. So tiny devices are in charge of performing that signal processing task. So there is no PC, no laptop, no tablet inside the brain so that you can run the signal processing process on it. So you have to have a tiny system in charge of everything, signal processing and the other functions that are expected from the system. There might be some opportunities in addition to the restrictions that you saw in the previous slide. So depending on the application, you might be able to extract some components of the signal and not just send the whole signal, which demands for so much bandwidth. Signal specifications are sometimes opportunities for us. So depending on the wave shape, on the content of the signal spectrum, and also the sparsity of neural signals more specifically, we might be able to propose some approaches for signal processing in biomedical implants or brain implants. This way, I can conclude that signal processing is one side of the coin and the other side is hardware implementation. From the standpoint of a circuit designer, a system designer, taking advantage of signal processing approaches, I can categorize the approaches that are available in the literature in two classes. The first is hardware embedded signal processing, where you embed the signal processing task inside the circuit that is in charge of some other tasks in the system. And the other one, which is common in the realization of signal processing techniques in biomedical implants, is just simple hardware implementation. Not simple, well, it needs to be efficient in terms of let's say time or maybe speed, hardware implementation, maybe power and physical size, but we are looking for hardware implementation approaches to realize the signal processing tasks. Let's take a look at signals. Signals in general have some contents, information. Sometimes the information is not concentrated anywhere along the input signal amplitude. So you don't care where the information is located, so you have to process the entire amplitude range of the signal in the same way. But sometimes information is concentrated at low amplitudes, and some other times you are after the information that are located in higher amplitudes. So it might change our approach in signal processing if we know the exact signal that we are going to process. For neural signals, most of the information is in higher amplitudes. So the background noise is just noise grass. There's no important information there. So if we are after the information that are at higher amplitudes, we need to use some compressive functions. It can be located or inserted between some blocks that are in the system, so you can have a compressive function between the amplifiers that do signal preconditioning in analog fashion, or maybe some other places afterwards. So if you combine the amplifier with a compressive function as its characteristic function, you're going to have a nonlinear amplifier or logarithmic amplifier. The other option that has been already tried is nonlinear ADCs, so that this function is embedded in the input-output characteristics of the ADC. So these are hardware-embedded compression techniques that are being used in brain implants. Let me skip this slide by just talking about two halves of a characteristics that are required for the processing of a neural signal. Supposing that the signal is located around a baseline signal, which is usually 0, because the LFP low frequency contents of the signal and also the DC component is already rejected when you are processing the signal. So the signal is located around a baseline, and this is the baseline. So two halves symmetrically located here are being used. And also, if you are doing quantization, then there's going to be a quantization noise as a result of using these characteristic functions. So the idea, most of the works that are being talked about here are the ideas from my students in my lab. Mr. Judy proposed that instead of using a linear quantization function, we can use an exponential or anti-logarithmic characteristics for the digitization of neural signals, as you see here. The advantages, data reduction. So number of bits for the ADC will be reduced by, let's say, 2 out of 8 if you use this kind of function. Noise reduction. As you see here, and will be explained later in the next slides, this part of the signal is not being digitized. So most of the background noise will be rejected or removed. And also, because of the realization of this technique in hardware, we are going to save area and power, which are also important. And this is an approach that looks into the specifications of the signal. So a signal-specific approach. And as I said, this approach is being embedded inside an ADC that is regularly used in biomedical implants to digitize the signal. So the ADC does both digitization and compression. We need two half-range ADCs. We combine these two in hardware and use both in addition to an extra hardware to come up with the digitized signal. This is the input-output characteristics of the signal, and this is the quantization noise, which is large at lower amplitudes and becomes very small at higher amplitudes, where the resolution is really important for us. Well, we introduced a parameter, noise content reduction ratio. When the signals comes through this process, the noise content of the signal will be reduced, and this is great. So we are denoising signal in addition to compression, in addition to digitization. And there's an interesting point here. Usually quantization noise is not welcomed. Usually we are running away from quantization noise, but just take a look at this graph. Well, quantization noise is here with the dashed lines, and the background noise overlaps so much with it. So this means that what is quantization noise? Loss of some part of the signal information. So if these two overlap, then it means that we are getting rid of the non-useful background noise. So quantization noise is exceptionally welcomed here. Well, to realize a nonlinear function, we use piecewise linear techniques and then successive approximation register. ADC is designed specifically for this nonlinear function to bring the signal back from the logarithmic space to the linear space. We're going to need a logarithmic if you use an anti-logarithmic ADC, then you have to have a logarithmic DAC with exactly the inverse function so that you bring the signal back to the linear space. And this is the IC that has that ADC on it, and that was tested using pre-recorded neural signals. And as you see here, this is the original signal, and this is the denoised signal brought back to the analog space after reconstruction. Okay, so that was just an example of hardware-embedded signal processing techniques. I'm afraid I have just maybe a few seconds, huh? So I'm glad that I was able to explain at least one example. So let me just go to some place so that I can conclude. May I have a few minutes more? Okay. I just skipped compression using discrete wavelet transforms. So there are different examples, different ideas to compress signal using wavelet transform in the discrete form. All of them do compression in the time domain. So they do compression according to the information that is inside a single channel and then the other channel. But thinking out of the box, one of my students proposed spatial compression. And that was because when you're doing neural recording, when a neuron fires, footprint of this firing will appear on so many channels, maybe more than 3-4 channels. So we have redundant information. And she proposed whitening transform as a kind of spatial compression in addition to temporal compression. And that way, we can boost the compression rate by a factor of 2, 3, 4, depending on the design. And there are so many circuit level and system level concerns that unfortunately don't fit in this very limited time. So I'm going to just conclude with this very last slide. Signal processing in neural recording implants cannot be thought of without hardware implementation. Operation in the real-time, area-efficient, and power-efficient implementation in the circuit level are necessities to realize signal processing techniques, and we can take advantage of the situation, not only in neural signals, but in any other application that might be of your interest. Thank you very much for your attention. I'm open to questions if there's time. To the benefit of being on time. Thank you.